So you're going to quickly notice if you look at this first bullet point that we're still going to be talking about series here, but we're going to change things up a little bit. We're going to introduce the idea today of Taylor polynomial approximations. In doing that, we're just going to really quickly introduce what a power series is, and that's going to kind of run underneath the surface for today's video. We'll come back to this idea of a power series more, and we're going to be talking a lot about it, and we're going to be talking a lot about series, so we'll try and remember all of our series testing stuff that we've been thinking of. We'll also do a recap of linear approximation, and then we'll extend that to general polynomial approximation using Taylor polynomials. So we'll build up what those things are. Then we'll give a brief little discussion of remainder and error for these polynomial approximations, but mostly we'll just end up talking about Taylor's remainder theorem at the very end of this video. And that's something that we'll bring back later on when we talk about not only Taylor polynomials, but an infinite Taylor series eventually. So first, let's talk about a power series. Power series is a pretty easy thing. It is a series of power functions. With coefficients. So notice that these kind of look like polynomials, right? Except that k goes up to an infinity on these. So this is a little bit strange. You could think that this almost looks like a geometric series, right? It's something raised to the k, but that something is x. It's an unknown variable. So it's almost like this is a function that's going to take in x values and all that stuff we're going to investigate a lot later on. More generally, we're going to add some sort of a shift, a center here to these polynomial things that we're building, or these power series, and we still have a sequence of coefficients where those coefficients can just be anything that we want. It doesn't really matter as long as they're real numbers, and we call this a value the center. So notice that the partial sums of these, this would be like this, we'll say, although I think it would be the, we'll just call it up to n. Who cares? This would look like c sub k x minus a to the k, and this would be c sub 0 plus c sub 1 x minus a plus all the way up to c sub n x minus a to the n. And so it's just an nth degree polynomial because it does end up cutting off. Cool. All right, let's do a quick recap of linear approximation. And it's going to feel like we don't talk about power series much, but they will come back, I promise. Maybe not so heavily in this video, but we will talk more about them. Linear approximation from Calc 1. Maybe you saw it looking like this. Exact same thing. All I've done is flip the order on that addition. No big deal. But this is really just point slope form of a line, right? So what we really have is the equation of a tangent line. And the picture that you probably saw in Calc 1, or that we should at least have in our mind, is that we have some sort of a function here looking like this, and we can go ahead and build a tangent line maybe right around there. We'll call that the center. And if we build a tangent line, then as long as you're close to that center, maybe like within this area, we might say that a point on the tangent line and a point on the graph at the same x value are pretty close to each other. So we can use the tangent line to approximate the graph. And we know that this happens close to the center. Our linear approximation is approximately equal to the function close to that center. This works for nice functions, and what I mean by nice is continuous and differentiable. We have to be able to draw these tangent lines, and so having that differentiability is what allows this property of local linearity, which means that as you zoom in on a function that's continuous and differentiable, it ends up just looking like a straight line. These linear approximations work really, really, really well for functions, or maybe I'll say at points on functions without a lot of curvature. But if you have a lot of curvature, then your function deviates away from the line quickly, and so suddenly close to the center doesn't mean as much as if our function wasn't super curvy, right? If we have a function that looks like this, and I draw a tangent line right here, it's not very close to my function for long. But if I draw a function that looks like that, and I draw my tangent line, I'll make it a straight line actually, then hey, my tangent line matches up with my function quite a bit in the middle here, or at least it's really, really close. So curvature is going to impact our approximations. This last little thing that I've added in is really important. At the center of our approximation, notice that L of A is equal to F of A. Oops, let me get rid of my straight line tool. There we go. L of A is equal to F of A plus F prime of A times A minus A. All I've done is plugged in X equals A, and you'll notice that this becomes 0, and so we're just left with this. So L of A and F of A are equal to each other. Well, that's good, because we're saying the Y value at the center is equal to the Y value of the tangent line at the center. It's kind of obvious, right? Our tangent line touches our function there. And then also we have that L prime of A is equal to F prime of A. If we look at L of X, that's F of A, constant, plus F prime of A times X minus A. There's our linear term. If we look at the derivative here, F of A goes to 0. X minus A is going to get multiplied out, and we have an F prime of A times X and an F prime of A times A. Or you could do the chain rule here. You could say this is F prime of A times 1. So L prime of A is equal to F prime of A. And that, again, makes sense because our tangent line slope is the same thing as the slope of the point at the center. That's kind of the point. All right, really quick example here. We can build a linear approximation of this square root function to estimate the square root of 3.6. So maybe a good center is 4, because the square root of 4 is something that we can get to. F of X is the square root function, so that means F prime of X is 1 over 2 root X. You can check that if you want. Make sure. F of 4 is an easy one. That's the square root of 4. That's 2. F prime of 4 is 1 over 2 root 4. That's a quarter. Okay, so what we have now is a linear approximation function where the slope is a quarter. Our center is at 4. Oops, I wrote A on accident here, and I want a 4 there. And my Y value is 2. I can multiply all this stuff out, and I've got a quarter X minus 1 plus 2. That's plus 1. What we're saying now is that L of X is approximately equal to F of X for X values close to 4. So in this case, a quarter X plus 1 is approximately equal to the square root of X for X values close to 4. And so we could say a quarter of 3.6 plus 1 is approximately equal to the square root of 3.6. A quarter of 3.6 is 0.9 plus 1. So we've got that the square root of 3.6 is approximately equal to 1.9. Is that a good approximation? I don't know, maybe. Maybe it's not as good as we would have hoped. We could pull up a calculator and see what the square root of 3.6 is to more decimal points, and maybe we'll find that like 1.9 is okay, but it's not great. So we could go ahead and try and find a better center for this. You could look at the square root of 361 over 100 as a better center. Because both of these are perfect squares. 3.6 is equal to 360 over 100. And so you can see this is off by not very much. So I don't want the square roots, actually. I want just 361 over 100. Because this is a perfect square. This is 19 over 10 if you square root this. 19 squared is 361. So you could go ahead and do that, but my guess is that that's not very obvious. So maybe when we see this 3.6, it's reasonable to just jump to the fact that the center might be 4. Now that leaves us with a center that's further away from the x value that we're looking at, and so we say x value is close to 4, and maybe this isn't as close to 4 as we would like. So how do we fix it? How do we get a better approximation? Well, the easy answer is to, instead of fiddling with the center, try and use a polynomial to approximate this. So we're going to extend our idea of linear approximation to a polynomial approximation. This is what our linear approximation looks like. And what we're going to do is call this our first degree linear approximation. So we'll say, all right, p sub 1 of x is equal to f of a plus f prime of a x minus a. And we've got these two properties that we talked about earlier, where the y values are the same as the function's y values, and the slopes are the same as the function's slopes. And what we're going to do now is see if we can build a quadratic approximation that holds similar properties. We're going to go and say, okay, a quadratic approximation is just going to include a quadratic term with some coefficient. We'll call it C2, the coefficient on the second degree term. Notice we just are adding that to our linear approximation. So we're just adding the second degree term to our linear approximation. And what you might notice, I'm going to go back to power series for a second, is that this is the second partial sum, S sub n here, or S sub 2, sorry, here, of all of the indices from 0 up to 2. So what we want to do is figure out what that coefficient actually is. This is the way that we're going to do it. We know that this is the general form of our quadratic approximation. It's this linear approximation plus a quadratic term. Made sure that we're centered at the same center. We want these properties. We want the y values to be the same. We want the slopes to be the same. But now, since we're talking about a second degree term, we also want the concavity to be the same as the function's concavity at the center. So the first two things are essentially the same requirements as the linear approximation, but now we want not only the slopes to be the same, but the concavity, the curvature of our function to be the same. So, oops, I got to work this out. So let's go ahead and just check this part. Let's check out what p sub 2 of a is. That's f of a plus f prime of a times a minus a plus whatever c2 is times a minus a squared. Well, notice a minus a is 0. Oops, that's a terrible brace. Let me fix that. A minus a is 0. And so what we're really just left with is f of a. Check. All right, let's try the second requirement that we have. P sub 2 prime of x is equal to, that's a constant, so that goes to 0. This is linear, so we just have f prime of x, or sorry, of a, plus the derivative of this quadratic term is 2c2 x minus a. And now we can evaluate this at a, and that's f prime of a plus 2c2 a minus a. That goes to 0, so we just have f prime of a. So good. Our first derivative evaluated at the center is equal to the function's first derivative. Now let's take a look at this last requirement about second derivatives. We'll say the second derivative, oops, I've got my straight line tool on. I always leave that. The second derivative is the derivative of f prime of a, but remember, that's not f prime of x. That's already the first derivative evaluated. That's just a number. So it's going to be 0 plus, this is linear, so we just look at the coefficient 2c2. So we want that p double prime of a is equal to f double prime of a. And that means 2c2 is equal to f double prime of a. And now we can solve for that constant. c2 is going to be f double prime of a over 2. So what we really have is that our second degree polynomial approximation is f of a plus f prime of a x minus a plus, yeah, I've got room, f prime of a over 2 x minus a squared. That way, when you differentiate everything, oh, that's f double prime, sorry. When you differentiate everything, all of the derivatives up to the second derivative will match with the function's derivatives up to the second derivative when they're evaluated at the center. All right, let's do the cubic approximation. What you're going to do, I'll let you do this on your own time, is check that all of these three are still satisfied. What we want to do is figure out what this third coefficient needs to be to make the third derivatives match up. So let's just find the third derivative. Oh, that's supposed to be a 3. There. This is going to be 0 plus f prime of a plus 2 f double prime of a over 2 times x minus a plus 3c3x minus a squared. Immediately, we'll find the second derivative. That's going to be 0, because the first derivative of this constant will be 0, plus, this is just f double prime of a, and it was linear, so we have a constant derivative now, and then we have 6c3x minus a. And lastly, if we look at the third derivative, this is just going to be 6c3. And what we want is for 6c3, that's this third derivative evaluated at a, to be equal to f triple prime of a. And so hopefully you can see pretty easily that this next coefficient is our third derivative divided by, 6. So p sub 3, the third degree polynomial approximation, is f of a plus f prime of a x minus a plus f double prime of a over 2 times x minus a squared plus f triple prime of a over 6 times x minus a cubed. Now what I want you to do is think about where that 6 came from. It was the coefficient on C3 here. Oops, I erased instead of highlighted. And that came from right here, which came from here, which came from 3 times 2. So what this is really this third exponent multiplied by the exponent lower than that, and then multiplied by 1. So you can hopefully extend this pretty easily to a Taylor polynomial. A Taylor polynomial just uses these same requirements to build an nth degree polynomial. So what you'll notice is that if we have some function where all the derivatives that we're going to want up to the nth degree or nth order derivative are defined, they don't have any problems with differentiability, then we can find this Taylor polynomial for f centered at a. Sometimes we'll call it p sub n for polynomial, but sometimes you'll see it with a capital T for Taylor. And what you can see is that it's the same formula. Notice it's f double prime over 2 factorial, that's 2 times 1, and then we'd have f triple prime of a over 3 factorial, x minus a cubed. We'd have the fourth derivative evaluated at a over 4 factorial times x minus a to the fourth, and we just go up however far we want, up to n. And you'll notice that you can write this as a finite sum right here, and that's not too hard to write. So the thing that we're noticing is that these coefficients are dividing by these values that come from all this power rule, right? All these exponents are being brought down out front and multiplied. So that's all that's going on here. All right, so take a second, find the third degree Taylor polynomial approximation for the natural log of 2. What we want here is f of x to be the natural log of x. We need a center, a. I'll give you a hint, make it 1, because your natural log function is defined nicely at 1. And we want to find the third degree Taylor polynomial. So that means you're going to need f of x, you're going to need f prime of x, you're going to need f double prime of x, whoops, and we're going to need f triple prime of x. You're going to build a polynomial approximation, and then you'll evaluate it at 2. So take a minute, see if you can figure out how that goes, and that should go pretty well. So hopefully this is what you've got. Here I found all my derivatives and evaluated them at the center, 1. And so I've got these little coefficients. But, oops, I forgot to do the division, right? Silly me. But I was just about to say, you have to remember to divide by the factorials. There we go. I can rewrite this then. And this is really x minus 1 minus half x minus 1 squared plus 2/6, or really 1/3 x minus 1 cubed. This is your third degree Taylor polynomial approximation. Or if you wanted, you could call this p sub 3 of x. And what we know is, just like for linear approximations, t sub 3 of 2 is approximately equal to the natural log of 2. And so t sub 3 of 2 is just 2 minus 1 minus half 2 minus 1 squared plus 1/3 of 2 minus 1 cubed. That's 1 minus half plus 1/3. That is approximately equal to the natural log of 2. What is that actually? 1 minus half is a half, and then if you take a half plus 1/3, that's 3/6 plus 2/6, so that's 5/6. So what we've found is that the natural log of 2 is approximately equal to 5/6. Cool. There are lots of examples online of people doing Taylor polynomial approximations, so feel free to mess around with those. But we should get relatively comfortable building these things. Don't forget to divide out your coefficients by factorials when you set up the polynomial. All right, I wanted to show you something on GeoGebra, which I think is pretty cool. This is a little applet that I've made that hopefully will help us when we're understanding what we're actually doing here. All right, so here I've got my linear approximation of my natural log function centered at 1. So here's my degree of the approximation. We can see that it's a straight line. This would be something that you would do in a Calc 1 class, where you get that the natural log function is approximately equal to x minus 1. What we want to do now, though, is take a look at not the second degree, but the third degree approximation. There it is written out. It's kind of annoying to read because the automatic output is annoying. But what I want you to focus on is how much closer our approximation is to our function. Let me go back to a first degree, and we can see that, like, right in this area here, our tangent line is close to the function. And if we bring that up to a third degree, it seems like the function follows this, or our polynomial, follows the green function a little bit more, a little bit closer. And you can imagine if we bring this up to a 5th degree or a 7th degree or an 8th degree or whatever, it seems like we're following this pretty closely. But then you'll notice that on all of these, it ends up kind of tailing off right around 2, right? We don't get much past that. But with that asymptote on the left, it seems like we do get actually a little bit closer. Log functions are a little bit weird. Let's take a look at just a completely different function and see what these Taylor polynomials are doing. This is one of my favorites. Let's take a look at the sine function centered at 0. You may have done this in a Calc 1 class. The linear approximation of the sine function centered at 0 is just x, meaning for small angles, sine is essentially the angle. If we bring this up to a cubic polynomial approximation, look at how much closer our function follows that green sine curve. Notice if we add a 4th degree, there's nothing really there. That's kind of strange. But a 5th degree, oh boy, that really starts following it quite a bit. And up to a 7th degree, and it looks like we're matching up in the middle really, really well, and we're deviating maybe around 3 and -3. So maybe this is pretty good for like any value between -pi and pi. That's not even that close to 0 anymore. So what we're doing when we extend the degree of this is we're really, in this case at least, opening up the interval of possible x values that mean close to center, right? We're giving ourselves a little bit more wiggle room here, where if you're not actually that close to the center, it's no big deal. This polynomial approximator seems to follow the sine curve really closely in the middle there. So we're not going to deviate that much. We could go ahead and reset this back and take a look at the cosine function, and you'll notice some interesting behavior here. The linear approximation is actually constant. And if we go up to degree 2, like you could expect, maybe we've got this parabola right in the middle, sending its way down. And then if we look at a 3rd degree, nothing happens. We don't add anything. And a 4th degree seems to follow it quite a bit. Another odd degree where nothing happens. And here's an even degree 6, and it seems to follow it quite a bit. Build it up to a maybe 10th degree polynomial. And again, look how closely this orange approximator function follows our green cosine function. This little applet is linked on Canvas. If you're in one of my classes, you should be able to find it on the course management site stuff there. And so feel free to play around with this. Throw in some other functions, change the center, mess around with the degree, and you might see some interesting behavior where this approximator either follows the function really, really well or maybe not, and we can kind of mess around with that a bit. Okay, so that's visually what's going on there. And hopefully you notice that while in a lot of those examples, our approximation follows the function pretty closely for a while, it's not perfect, right? There's some sort of an error there, a remainder that's left over, some excess bit. So let's introduce this idea of remainder and error. We've got some function that's approximately equal to some polynomial for x values close to the center, whatever that means. Maybe we have a lot of wiggle room there, maybe not a lot of wiggle room, but who cares? So maybe I'll put this in quotes again, close to the center. So what we can do to change this approximation to exactly equal is to just add an error. Say, all right, our approximation is off by some unknown amount. And if we knew exactly how much our approximation was off by, we could add that in and get the real answer. Doesn't make a lot of sense to do in practice, though, because if we knew how far off our approximation is, then we know what the actual answer is, right? So this is like an unknown error, but there is some value that you could add to our approximation that will give you the real honest-to-goodness answer. We hope that that error is small. We're going to call it the remainder. The remainder is going to be some r sub n. So if you have like a second degree polynomial p sub 2, then the remainder that's left over is r sub 2. If you have a 10th degree polynomial, then the remainder is r sub 10 for that function. And so if you add in that remainder at x, whatever that is, it's unknown for us, you'll get the exact value. So this is some unknown value, some unknown remainder. We can't really get at it, but what Taylor did was build this remainder theorem, and it's a really cool thing where it actually gives us the value of the remainder. It's unknown. It's going to be based on c. So let me read through the theorem here. We've got some function that's got continuous derivatives up to the n plus first order. So n plus 1 derivatives are all good and continuous on an open interval containing your center. For all the x values in that interval then, we know that the function is equal to whatever that polynomial approximation is plus the remainder, where that polynomial approximation is the Taylor polynomial like we built earlier, and the remainder is specifically this. The n plus first derivative of f evaluated at c, notice that's different, over n plus 1 factorial times x minus a. For all of our Taylor terms, you might remember that that was like the nth derivative evaluated at a over n factorial times x minus a to the n. We evaluate at the center. Now this is not the center. It's some point in between x and the center. The proof of this is very difficult, and it's beyond the scope of our course, but I'll give you a little bit of insight of what's going on. This is kind of like a point that was guaranteed to exist by the mean value theorem, meaning it's somewhere in between and the derivative at that point matches up with some average rates of change and things like that. So you can kind of think of this C as some sort of mean value theorem point where it just so happens that that next derivative evaluated there gives you everything that you want about that remainder. You don't need any more terms. So what this is it looks like the next term in your Taylor polynomial if you were to extend it by one more degree, but instead of evaluating at the center, we're evaluating it at some point close to the center, or maybe between x and our center, where x is every x value in our interval. So as you get closer to the center in the x values, that c is also close to the center. And so that's how that one goes. We're not going to do too much with this remainder theorem yet. We are going to do something a little bit later, and hopefully you'll recognize that as n goes to infinity on this thing, this remainder is going to get small. So that's something that we'll play with a little bit later on. But for now, get some practice playing with these Taylor polynomials and using them to approximate some weird function values. They're going to be better approximations than we ever had in Calc 1, so have some fun with that.